Hello, everyone. Welcome to the fifth L paper discussion on Attention is All You Need. My name is Simrat Hanspal, and I will be your moderator for today's session. A quick intro about me. I have a career spanning over a decade in the AI ML space, specializing in the natural language processing. Currently spearheading AI product strategy at Hasura. I'm fortunate to have worked and led AI product teams at renowned organizations such as VMware, Five Money, and Nirvana Insurance in the past. Our presenter for today, Mahati Bhagavatullah. Mahati has master's degree from Triple IT Hyderabad and has been diving into data science for past 10 years with special focus on NLP. She's worked on very interesting projects involving knowledge graph, variational autoencoders and decoders, active learning, and more. She's also led a team of data scientists to create impactful products. More recently, Mahati has been working with large language models. If you find legal documents complex to process, good news for us. Mahati has released an open source LLM application for answering legal questions, and it's called Lawyer GPT, which has a very quick turnaround time. Lately, she's been teaching data scientists about LLMs, fine tuning, and RAG models, and even started building her own LLM agency, working with clients from US and Israel. The fifth elephant paper sessions are curated by Bharat Shetty along with the Gen AI community, experts, and researchers. Bharat has worked at Airtel Labs, Concert Health AI, Fiber, and many startups and companies across diverse verticals in the space of conversational AI, IoT, healthcare, edtech, and genomics. He currently consults on AI, ML, and backend engineering. The paper discussion session aims to foster a community dedicated to demystifying research papers through a practical, code-centric discussion method whenever possible. The session will be held once every month, either online or offline. Thanks to Hasgeek for providing us with this platform. Fifth L Winter Edition is starting on 8th of this month. Check out the Hasgeek website for more information. Few points about the Q&A moderation. We have scheduled time check-ins at 30 minutes and 60 minutes into the session where we will take relevant questions. We will also have Q&A session at the end of the session. Please post your questions on the Zoom chat and I'll try to answer them or queue it up for the Q&A session. Sorry about that. Do check the already asked questions before putting your questions, as it will help us speed up the session. Encourage minority participation. We encourage women, persons of other genders, and people with disabilities to ask questions and actively engage their participation via these platforms and groups. You can DM me on Zoom if you have any suggestions or comments. Just a moment. I thought I had enabled Do Not Disturb. Yeah, just bad timing. So let's get back. Let's talk about why is attention important and why are we having this paper discussion today? Well, building meaningful applications with natural language is a difficult task. You have to look at, sorry, this little bit of an IT issue going on my end. Yeah, so let's talk about why attention is important as a concept and why are we discussing this paper today. Well, building meaningful applications with natural language is a difficult task. We have to look at both the word for the local context and the complete sentence for the global context. Even then, sentence is not enough to convey the complete meaning. For example, I'm going to the bank. Are you going to the financial bank or the river bank? Well, we all know language is complicated. There's so much variations that we can see. And we also knew that token-based modeling wasn't going to take us far. In short, we were all waiting for the transformer moment where models trained on large corpus of text have reasonable understanding of the language and can process language similar to the way humans do, by placing attention on relevant words. The birth of transformers with attention led to an explosion of innovation in natural language space. Even the chat GPT is based on the transformer architecture. So without a further ado, let's kick off this very exciting session. Over to you, Mahati.
Thank you, Simrit. Thank you for a very wonderful introduction. And yeah, let me actually share my screen. I hope everyone could able to see the screen.
Yeah, we can see your screen.
Yeah, thank you very much. So yeah, before I start, I also have to thank Hasgeek for giving this platform, and then letting this wonderful paper get letting me also to say about this wonderful paper. Thank you very much, Hasgeek, for this wonderful platform. And yes, when we get into the paper, attention is all you need. Now, very frankly, we don't need quite a good introduction for this paper, because this is one of the transformative papers, especially in the field of natural language processing. Because this has actually, there is something called as an era before and after this particular paper has actually, this particular paper. So let's get into detailed versions. So let's actually look into the era before transformers. Now, the first thing, there was in around 2013, there was this kind of a movement like golden period for the image related data, wherein the deep learning technologies, something like convolution neural networks, CNNs, were actually working very nice with given any particular task. It actually used to won many competitions, one among them being ImageNet, and it has actually able to understand the images, give the attention, and do many tasks, especially with respect to the CNNs. But that moment was not yet been there was not much of an improvement with respect to the NLP area at that point of time. But there were baby steps towards getting into something called as word to vec in around the same period of 2013, wherein wherein the words have been converted into embeddings. So that was one of the revolutionary idea, I should say, wherein the words are actually being converted into embeddings using word to vec kind of architectures. Now, post that in 2014-15, there was even a better architecture called as recurrent neural networks, which apart from getting the embeddings, it could able to solve many of the use cases like classification, like sequence to sequence models, like translation, summarizations, and so on and so forth. So when this particular RNNs were actually been present, they could, in the NLP, they could able to solve many of the use cases as I just mentioned. But then there were some limitations which we will come in a minute. So in and around 2015-16, from this recurrent neural networks, there was a beautiful concept released, which is nothing but the attention. Rather than looking at all the words in your sentence and then predicting a classification or a sequence to sequence model, there is an option of you looking at specific words and then predicting your result. That was a concept of attention in around 2015-16. Now, this attention concept has been used on top of your LLMs and LSTMs, and then could able to get good results. But as I just mentioned, there is one major problem with RNNs, which is nothing but sequential processing. Now, any of the architecture till this era of 2015-16 was actually processing the sentence sequentially, which is nothing but taking one word at a time and then getting the result. Now, when you are actually doing such a sequential processing, though the results were actually coming out good, but processing high dimensional data was very difficult. So to an alternative for this solution, what people have actually started doing is relatively convolution neural network is parallelly processed than recurrent neural networks. So they've picked up the convolution neural networks and started working on the NLP related tasks. Something like conf S2S, where it is actually a sequence to sequence, sequence to sequence on with convolutional neural networks, or ByteNet, where it is an encoder decoder on like convolution on an encoder and decoder kind of an like architectures. But then, unfortunately, there is the computation over in this scenario was also not that efficient, and also the long range dependencies. Now, if I'm actually having one particular context in the start of the document and another context in the end of the document, the long range dependencies, this context has never been captured using even these intermediate solutions with parallel processing. Then it is a bang on moment, which is transformers. The transformers has completely removed this sequential processing from its architecture and only relied on attention layers, and hence could able to not only do the processing nicely, could able to access could able to get a large amount of data, process large amounts of data, and also do multiple tasks on top of it had multiple advantages on top of its previous networks. So let's see what are all these multiple multiple applications which were actually good with transformers when compared to its previous architectures. One being, as I just mentioned, the parallel processing. Now, irrespective of it is not necessary that the architecture has to read the first three words to process the fourth word. It can actually process all the words simultaneously. This has actually helped for important aspects, which is nothing but a scalability and the GPU utilization. Now, if you can scale transformers to whatever extent you want to get into, as we can actually see today, you can say to the trillions of tokens, and also utilize your GPU properly, such that you can actually process them, all of them parallelly. Then transfer learning from the from the previous architectures, though to a certain extent they were actually also doing transfer learning, but transformers were actually doing the transfer learning very nicely. So you teach transformer one task, but it can do multiple tasks on top of the task you have already thought. Anyways, it will actually do the task that you are actually it has been trained for, but also does many other tasks related. Transfer learning being one of that. Interpretability. So, it is not just it will only not just give you the results, but it will let you know what part of the results, what part of the words, or what part of the sentences are actually getting to that result, which is nothing but the attention. So because it could actually able to say what parts is getting into that particular result, it is more interpretable. You know that why is this transformer working this way. Long range dependencies. Now, as I just mentioned, if I'm actually having one particular context in a start of my document and another particular context in my end of my document, this long range dependencies within a particular document is also being captured nicely in the transformers. Language agnostic. Now, as an language agnostic feature was already been present even in the before architectures as well. Transformers were a little more efficient in doing this. Now, language agnostic is nothing but it can process multiple languages at the same time as well. Multimodal. Again, you can actually train your transformers with images, videos, textual data, speech data, whatever it is, and also simultaneously all kinds of input text can be given to your transformers and train them. Such a such an architecture as this architecture can actually support even in multimodal scenario. So this being the major distinguishing features of transformers. Now let's get into what made transformers, what architecture of the transformers is actually helping it to solve all these problems. Now, to start with, So in this particular architecture, though we will actually jot down into each and every step of the architecture, like input embeddings, positional embeddings, the encoders, decoders, the attention, feed for a network, add a norm, softmax, every bits and pieces of the architecture is something we'll get into deep depth of it. And then we'll see also intuitively, as in why is this actually working in a certain sense. Now, coming to the input and the positional embeddings. The embedding layers first. What is an embedding layer? Now, your embedding is nothing but the ultimate understanding, obviously, of a particular input. Let that input be image, text, video, whatever it is. But in the context of attention is all you need paper. The problem statement that has been picked up is sequence to sequence problem statement, wherein it does solve the mission translation task, wherein I give the input in one language and the output would be actually given in another language. That is the context. We'll get into the context as well in the later stage. But so the entire in this presentation, the entire concentration will be towards the input of text in itself, and then and then around the paper of attention. Now, getting into what the embeddings are, as we have just seen, it is in this architecture, if you see, input embeddings is nothing but an addition of the positional embeddings and the input embeddings. So what is input embeddings? It is just a learn layer, just an embedding layer that can be learned, it's just a neural network type that can be actually learned through the learning. What is positional embeddings? Now, positional embeddings, the concept of positional embeddings is needed in transformers. The reason behind is that because we are processing the entire data parallelly, but I mean, as I just mentioned, there is no need of the fourth word. There is no need of the first three words should be processed for the fourth word to be processed. Now, if we are actually doing this parallel processing, we actually need at some point of in some place the position being given explicitly, that you see this is at the point 0, this is at point 1, this is at point 2, this is at point 4. So that layer which would actually give this kind of an explicit information that this particular word is present in a particular position is usually being given by positional embeddings. Now, that is nothing but to mark a relative and absolute position of words within a sentence. Now, why are we actually using over here? If you see this input embeddings, which we actually learn through the entire network, they will be little shifted towards the positional embeddings based on its own position, such that you would actually get a word along with its positional embeddings, such that it is learned appropriately, it is learned appropriately according to the context of given sentence. Now, what is actually positional embeddings? Now, if you can actually think in this way, that if I have to give a sequence, like let's say I'll give an example, I have a sentence, how are you? Now, if I have to actually give a particular position for each, I can actually give a how to be a 0, R to be a 1, and you to be a 2. But then in this scenario, what happens is if the length of the sentence is a very large, then the positions the number of the position would be very high, and then you can't embed into your own architecture. That is the reason why we are actually the paper has actually suggested for an embeddings for each and every word. Rather than giving a position number as 0, 1, 2, 3, it has actually given an embeddings. Now, what are these embeddings? They are nothing but sine and cosine functions alternatively. So, I mean, I'll actually show you pictorially, but then at a 0th position, if it is sine, if it is 1 position, it is cosine, and so on and so forth within a dimension. Now, why we have actually choose only sine and cos, the reason behind is that is the relative positions are being defined well with sine and cosine. So what I meant over here, relative position, if I'm having a word at 4th position, and if I'm having a word at 1 position, the relative positioning that these two are being two words apart is being correctly interpreted using sine and cosine functions, and that is the reason why the positional embeddings have actually chosen sine and cosine values for it. Now, how are we actually getting these embeddings? Now, if you see, I have a sine function with a particular slope. Now, just a second. Okay, I have a function with a particular slope. Then the values of this fine function will get into the first dimension, like 0.3, 0.1, minus 0.9 are the values from the first sine function. Then my next cosine function will actually give me 0.8, minus 0.7, minus 0.8, so on and so forth. Like the third function would actually give me 0.2, 0.9, 0.9, and then so the cosine values. And so using this alternate cosine and sine functions, the positional embeddings are being filled such that the relative positions of these words are being understood properly. And when you actually add these positional embeddings to your input embeddings, the proper alignment of your input embeddings will also be set according to their positions. This is how the internal positions are being taken care in the transformers, irrespective of their parallel processing. So, as we have just seen, we have actually seen the input embeddings and the positional embeddings. Now, I just actually want to go ahead. Please post your questions in case you have any doubts. Now, let's actually get into what the encoder and the decoder architectures are. Now, what is encoder, what is decoder, and what are they meant for? Now, as I've just mentioned, in the context of attention is all you need, the problem statement that they're trying to solve is a missing translation. So if you can see in this scenario as well, we are giving something called as an input called as how are you, and the output is it would be something like aap kaise ho. So this is the missing translation problem that they're actually trying to solve. And though not for Hindi and English and Hindi context, like I have actually just made it a little more such that it is quite good for in our context, but it is not in English and Hindi. So in this architecture, as I've mentioned, there are two major blocks. One being an encoder block, the other being a decoder block. Now, what does an encoder block does? The main aim of encoder is nothing but it has to summarize the data and encapsulate it into embeddings. Now, I actually have a source language. How are you in this context, the English? The embeddings or the understanding of my entire source language has to be embedded into a set of vectors and has to be given to the decoder. That is the task of an encoder in this scenario. Now, what is the sorry about that? And what is the main functionality of a decoder? It has to generate the output based on these embeddings. Now, I actually got the embeddings, the understanding of my English language. How are you? Now, what are the relevant words in Hindi, and how can I actually project, or how can I actually generate the data in my Hindi language? That is the main functionality of the decoder, that it would actually take up the embeddings and generation. So in short, if I have to say, the task of an encoder is to summarize, and the task of a decoder is to generate the output. Now it is auto-regressive, which is nothing but it consumes its own generated outputs, and then actually based on that, it would actually produce a new output. So it is actually usually called as an auto-regressive model. Now, if we get into internal details of what the encoder is and what the decoder is. Now, what is the encoder? It is a 6 identical layers stacked upon one or the other. As you can see, encoder on top of an encoder. They are actually being stacked upon in this architecture of transformers. And then now each layer of this encoder would actually have something like this. You would actually have a multi-head attention, the feed forward neural network, like fully connected neural network, which we actually call as position wise fully connected feed forward layer, residual connection, and the normalization. Residual connection is nothing but the add over here, which has been specified as the residual connection, and norm is nothing but the layer normalization, which actually happens. There is a dimensionality of 512 maintained throughout the entire architecture. There's a reason why. I'd actually let you know in the coming slides. But the dimension of the entire model is 512 in this paper. Now, what is a decoder architecture? Decoder, again, is a 6 identical layers stacked on one another. And then the architecture of the decoder is something similar to what encoder is in a certain part, like multi-head attention, feed forward network, residual layer, and layer normalization. But the only aspect that has added upon is that a mask multi-head attention. Okay. A mask multi-head attention, wherein you would actually mask certain set of the input and then give it to the layer, which again I'll actually say in a brief in the coming slides. So in this scenario, what we have actually seen is input embeddings, positional embeddings, and the encoder and the decoder. Now, the important aspects of all these things is nothing but the multi-head attention, that being one of the important aspect of the entire architecture. Let's actually understand multi-head attention in a more intuitive way first, and then into a mathematical way. Now, I'll give a small analogy for understanding multi-head attention. Let's say there is a teacher and a set of students in a particular class. Now, a teacher has to actually, the task over here is the teacher wanted to pick some of the important students within a class. Now, how is she willing to do that? Now, the teacher is asking the students to do 3 tasks. One of which is the teacher is asking the students to raise their hands, whomever they feel are important for that task. So the teacher is asking the students to raise their hands. What is the second thing that the teacher is asking to do is to keep a special spectacles. This special spectacles, what it does is it actually would say how important are the other students in the class. So the specs color would actually vary based on the importance of other students in the class. That is the second thing the teacher is actually asking the students to do. And there's a third thing that the teacher is actually asking the students to do is to write in a particular paper how about the information about yourselves, as in what have you done, what is your name, what is your background, what are your favorite things, and so on and so forth, about entire bio of that particular students, and hold that information while studying. So these are the 3 things that the teacher actually asked students to do. Now, and based on these 3 things, the teacher have actually decided to choose which among the students are being important. Now, in this analogy, can you relate anything can you relate this analogy or this story to what we are actually looking for? The attention, is that okay? If you can actually type in or then say something. Okay. Wait. Okay. Yeah, to a certain extent, yes. So over here, if we can actually see this, this particular teacher that we are actually referring to is a model that we are actually talking about. And the students in this scenario are the words or tokens. So what the model is trying to do is to pick up the important words which are necessary for running a particular, a particular task. So the model is actually picking up the words or tokens. And the three things that have been actually asked to do are query, key, and value pairs. Okay. Query, key, and value pairs, wherein they would actually have this is a three interpretations of the same particular word. There are three interpretations, and then based on these three interpretations, it would actually the model would actually pick up which word is actually important, and the entire the entire the calculation based on query key would actually be your attention score, and the entire mechanism which has been actually used by the teacher would be your attention mechanism. Now, also intuitively, I just want to say over here that each model can actually have its own attention mechanism. There can be a situation that one particular model would give way more to the value information. One particular can actually weigh more to the query information. So each and every model would actually have its own attention mechanism. That is one thing. And the second thing, obviously, is that in the initial stage, when a teacher just entered a classroom, she might not actually have any information regarding any students. I mean, as the time passes, it get to understand the students. Similarly, does the model. Initially it would actually randomly assign, and then post the processing, it would understand the importance of the words, and so give the attention to that particular set of words. So this particular analogy, if we actually get into that self-attention, the concept in itself. Now over here, as we have seen, that these particular words or tokens are nothing but thinking, missions, and all these are the words. Now, if we interpret that a little more mathematically, there is this particular embeddings that we have just seen, the input and the positional embeddings that we have just seen. We would actually pass this input and input embeddings into a linear projection and get these three values: query, key, and values, which I'll also show a little diagrammatically in the later slides. Now, once I'm actually having query key values, which is nothing but, again, as we have seen, raising hands, special specs, and information and all stuff. Now, what we are actually doing is we are picking up the query and keys and generating the dot product out of it. The dot product is nothing but the score in this scenario. Now, the score, in the sense, the attention score. Now, this attention score is ultimately multiplied with your value. But before the multiplication with the value, we do a certain normalization, in a way, steps, which is nothing but scaling down and then doing softmax. The reason why we scale down and do a softmax is that these values of multiplied values are relatively very high. So multiplying these values, these higher values with the vectors is actually not advisable, like in the current setting. So we actually scale them down and then use softmax to distribute them between that 0 and 1 0 and 1 values, and then multiply them with the value vector. The summation, so softmax, and then summation, we multiply softmax with the value vector and then aggregate them. So summation of all these value vectors for a particular word. Over here, if you actually notice, we are only doing one particular word, like thinking, and then actually doing a matrix vector multiplications in this scenario with all the words related with all the related words. So if you can see, this can be parallelized. If I'm actually dealing one word at a time, you can parallelize your architecture, because I am, irrespective of where the word is present, we can still process the entire entire architecture. So so I'm taking each word, doing all my manipulations, projecting it, getting query key value vectors, and doing a dot product, scaling it down, and then multiplying with my value vector, and then aggregating all those vectors. So this all steps would actually be done using a particular, at a word level. So you can actually parallelize the entire architecture. Now, this entire process is nothing but the scaled dot product attention, which has been mentioned in the paper with the given formula that attention of query key and value vectors is nothing but softmax, or softmax of query key transpose divided by scaling down with the under root of dimension, and multiplying the entire value with the value vector. That is what we are actually doing in the scale dot product attention. Now, as I just mentioned, the input embeddings have been sent through linear projection for query key values. Now, what is the sent through linear projection? It is nothing but you would multiply your input, input values with the weights. So again, this learnable weights, I should say, learnable weights, such that you would actually get query key and value vectors. That is why what you would actually do linear projection on the input embeddings and then get the query key and value vectors. Now again the same formula at a, so these two representations are at a matrix level. So you would actually do this similar transformations that we have done, a linear projection. Then we are actually doing the same things again, dot product, scaling down, softmax, and then multiply with your value vector, and summation of all will actually give you your z z vector. Now this is something called as a self-attention. If we are actually doing it with a one single attention to itself, if one sentence, if we're doing self-attention with itself, this is called as self-attention. Or if we're doing with a multiple sentences, when we're using one linear projection and all, this is called as a single head attention. Now, let me actually say this. What is, this is all about only attention. Now, what is heads in this scenario? What is multi-head attention? Now, again, going back to an analogy. Now, let's say I want to read a particular book. Now, when I'm actually reading a particular book, so rather than me reading a book, what I actually thought of is I'll actually call 4 more people. I'll give the book to these 4 people. Now, when I'm selecting 4 people, I'm making sure they are little divergent. One is a female, one is a male, one is a child, one is an elder person. So I'm actually giving this particular book to 4 different people and then asking them to read. Now, when they start reading, it is obvious that each and every person would actually give attention to different parts of that particular book. So one, let's say a youngster would actually give more importance to the fictitious aspects of the book. The old person might actually give attention to the values of the book, and so on and so forth. Each person would actually give importance to different aspects of the book. And then after they've completed reading, what I'm also asking them to do is come, sit together, read, discuss among yourselves, and then you gave me the summary. So when they're coming, sitting and discussing among themselves, then in this point of time, the knowledge transfer is also happening, and also the attention, which parts of the, even if one particular person has missed a particular point, the other people would cover. So ultimately, when I'm getting the summary, I am getting very attentive and overall picture of the entire book altogether. Now, this is the same thing which will actually happen in multi-head attention as well. Now, each input embeddings in the case that you have seen, thinking or missions or either of the one token, would actually get into different attentions. We have seen one calculation of scaled dot product attention in the previous set of slides. So the same thing would actually happen for different set of weights with different attention heads. Then overall, you would actually have different z-scores for each and every attention head. This is this is, as we have seen in the analogy, this is nothing but their understanding of that particular book. So in this scenario, it is their understanding on this particular set of data. Now what we do is we concatenate all these attention heads and multiply again with a weight matrix. Now in this scenario, what we are actually doing is we are actually making sure that they are talking with each other, the summarized version is what we actually need. So when we are concatenating, when we're multiplying with another weight vector, we would actually get the result, which is the summarized form of the entire input that has been given. So this way, the multi-head attention would actually help to get the entire overall picture of the entire data. So post this applications, we'll take a break in case it is half an hour and take up your questions. Now, how is this attention helpful in our scenario? How is this attention helpful? Now, in the encoder and decoder architecture, in the current architecture, where are the places where attention is helpful? That is, if that is the case, now we've given the encoder and decoder architecture. What are we actually doing over here is from the encoder, we are giving the key and value vectors to the decoder. And the query vectors are of the output are actually being given to the decoders. So what is happening here is with the key and value vectors, the entire essence, again, coming back to the mission translation application, the entire essence of my input language is being given to the decoder using the key and value vectors. Now the query vectors of the output or the target language, when I'm actually having the query vectors, that would actually have the essence of the target language. Now, using these two, the output is generated. So, attention over here is actually used in the while actually giving this key and value vectors. What words has to be actually been given more attention while calculating the output generation to decoder is being actually sent in this key value vectors. And when also getting the key vectors, what words again in the output vectors need to be given actually importance is being taken care in the encoder decoder architecture. Now, when it comes to only encoder, within the encoder, how is this attention used? The the generation of one output is dependent on the generation of the previous output. As we have seen, this is auto-regressive algorithm. So the generation of one output is actually being dependent on the generation of the previous output. So what words are being given attention in the previous words were also being of higher importance when we are calculating the attention of the new sentence as well. This is how the attention is used in the encoder architecture. Now when it comes to the decoder, I should say again similar to what encoder is, but the decoder generates the output. So aap kaise is something that has been already been generated, but now when I'm generating ho, and it is actually looking at the previously generated output, and then based on that, the attention, the words where the attention is given, and based on that, it would actually generate the output. This is how the decoder, this is how the attention is used in the decoder layers. So this is all about the attention. So I'll take a little break here, Simrat, if that okay, or shall I continue?
No, sounds good because there are a few questions.
Sure.
Yeah, so I think the first one was to get little more clarity on the positional embeddings. I think it's a little confusing as to how the architecture has tried to incorporate positions into this embeddings.
Okay, so you actually have positional encoding different from the input encoding, but when it is given as an input to the architecture, they are both combined, added on one top of another, and then actually given as an input to the architecture. If
Right.
I'm actually
Yeah, actually, this question comes from Prabhu. I'll also read out his question. He says regarding position embedding, how different position is captured. I did not understand the graph example.
Okay. So we have time, or shall we go to the slide?
Actually, maybe I can like really quickly touch upon that. So the challenge here was that because they wanted to combine the word embedding and position embedding by summing it up, they wanted position embeddings to be something that is manageable, distinct, deterministic, and also very small in number so that it doesn't change the word embedding too much. And so they were thinking of multiple different approaches to do that. One of the ways they realized was that if they use multiple different sine and cosine functions which have different frequencies, so you'll see like some functions are like they have like really high frequency and they're really short, some have like really low frequency. And if you just and on the x-axis you have the position, on the y-axis you have the value. So x-axis would mean like your position, and so if you just take the values from these different multiple plots, the sine cosine alternatively, and you generate this positional embedding, this will be distinct because you have basically taken the value of your position from different graphs. The final embedding that you will get will be unique to your position. So that is how, in a very interesting way, they came up with this positional vector, which is like really unique. At the same time, it has very small values between -1 to 1. And there was
So
another
adding
question.
upon the point, the only one aspect is the relativeness is also captured in this scenario. So the sine and cosine also is being chosen because uh, if I'm actually seeing u, if I'm taking the embedding of u and how, I know that u and how are being actually deferred by two positions. So that relative positioning is also been captured using, inbuilt within sine and cosine, and that is also one of the reason that sine and cosine has been actually chosen.
Yeah. And then that's a very interesting point. Like if you have another U word in the same sentence, because the position of that U in that sentence is now different, you'll like pick the different points on each of these graphs and you'll get different value for the second U.
Yes.
Okay. And so one question was, what are the dimensions in the context of this paper? What is dimension in the context of, I think,
Okay. Yeah, I'll get into the dimension a little later. I mean, I have a slide for that.
okay,
Yeah,
cool.
yeah.
I think then there are some more questions around the attention. We can come back to it at the last.
Okay. Sure.
Sounds good.
Sure. So when it actually comes about the dimension, I'll actually. So yeah, a few more slides. I'll actually let a small, a small understanding on the dimension as well. But then, as we have actually seen till now, we have seen the input embeddings, the positional encoding, the encoders, the decoders, and multi-head attention. Why are being used, and what is the intuition behind all of these things. And now apart from this multi-head attention, there is another layer which is also important, is nothing but position wise a fully connected feed forward network. Now, what is like, position wise fully connected feed forward network? It is nothing but a fully connected layer having a two linear transformations on one ReLU transformation. Now I'll just give a little understanding on this. Just like in just like any other neural network scenarios, right, wherein we actually why was the neural networks could able to solve all the problems nicely is because of its complex architecture. When it is a fully connected layer, what it does is it can understand the complexity of the data. Now, the complex understanding of the data, it can actually done it better and then give you a result. So that is what even in a normal neural network use case, like you can just consider a normal neural network as well. If it is fully connected, it can actually understand the complexity of the data. So the similar thing has actually been done even in this scenario is that apart from the attention, because attention was the basic idea of the attention is to pick up which words need to be actually given attention on top of the other words. So apart from this, there is another necessity of the algorithm also that to understand the data in itself. Now, this understanding of the data, apart from even the multi-head would actually do, apart from that, the feed-forward neural network also does this understanding of the complexity of the data. This is nothing but using a two linear transformations and one ReLU activation, general to what we actually do it in any other neural network, that you actually have an input X, you would multiply with a weight matrix and add a bias. Now, this is the usual, this is the usual linear transformation that we actually do. Then on top of it, we do a nonlinear activation. In this scenario, it is ReLU activation. We use max of 0 to this particular value. You make it a little nonlinear. And again, does the second linear transformation over here, which is nothing but multiplying a weight and then adding a bias. So as I just mentioned, the major intention of intuition, why we actually having this is to understand the data in depth. And the second part of it is, apart from the data, the position related the position related information is also being learned internally, though we will not explicitly give the position related information. But then if you can actually see in a particular matrix, x1, x2, x3, we are saying that x1 is being stated as the first position, x2 is being stated as second, and x3 is being stated as the third position. So when we are actually giving these position, and all the linear transformation and the ReLU activations are done on the same matrix, so row wise. So this each row has been treated separately and identically. Because of that, the position wise related information is also being learned. Also, the complexity of the data is actually learned. Since these are actually being learned together, this particular layer is actually being called as position-wise feed-forward network. I hope I'm actually clear over here. So, in this scenario, what we have actually seen is till the position-wise feedward, and now the small layer which is actually been remaining from the all the what I should say, all the network, all the layers is nothing but this add and norm. If you actually notice, this add and norm is actually being present after each sublayer. Will that be multi-head attention? Will that be feed-forward network? Would that be any of the layers? This particular add and norm, are being added after each sublayer. Now, what is this particular sublayer is all about? Now, you would actually have, add is nothing but the residual layer, which we call, which is nothing but it will add the output of the sublayer to the input of the sublayer. So there is a sublayer. The sublayers here, I mean, the multi-head attentions, the feed-forward networks, these two being the sublayers. Now you would actually add the output of the sublayer to the input of it. Now, why are we actually doing it? Is the learning of that particular sublayer is usually being stored in the output. So that output need to actually get back to the input such that the impact of the learning is reflected in the input layer. That is one of the reasons. The second being, in this humongous networks, there is a high chance of vanishing gradients problem. So the weight vectors would go zero at some or the other point. Now, when to overcome that particular feature as well, this residual addition is usually done in between after each sublayer. These being two reasons why we actually have this sublayer. Now, coming back to the point of dimensions. Now, dimension is nothing but we have an embedding. So, what is the length, I should say, of this particular embedding? Now, what we are calling the length of this embedding is 512. And we are maintaining this 512 across the architecture. The reason why we're maintaining this 512 length of embedding across the architecture or across the, across all the sublayers is because we have to do this residual addition here and there. Every time, because we're doing this residual addition, we are actually maintaining this 512 dimension. Now, I hope I'm clear with respect to the dimension part. Then post that, there is something called as layer normalization. Now, what is layer normalization? Now, after you actually have the output, this output will be given as an input to the next layer, obviously. Now, when you're actually giving the input, we make sure that we normalize this, output and then give it such that the basic idea is such that it can actually learn faster, it can actually converge faster. That is the only reason why we actually do a layer normalization before we giving it to the next layer. Hope I'm clear on the dimensions part and also on the residual and the layer normalization part. So with this, we could able to actually see these entire things input embeddings, positional embeddings, attention, the feed network, and the additional and normalization. Now, the part that has actually been pending is the softmax and the linear layers. Now, if you can actually notice, what is this particular linear layer is doing? We have an output from the decoder with and then this output has to be matched to the to the vocab size. So what I meant over here is I have an output of 512 dimension, let's say, but my vocabulary is let's say around 4 trillion tokens. Now that is my vocabulary, but let's say my this is not the scenario, frankly, but I'm just making up, because the dimension will not be so less if the token size is if I'm having so many tokens. But then approximately I'm saying if I'm actually having a dimension vector of 512 and then I am having 412 4 trillion tokens of my vocabulary, my entire data has 4 trillion tokens, words. Then to match this 512 dimension, that has to be transformed into this 4 trillion vocab size. Now, that is the main idea of what linear layer is doing. Linear layer is actually transforming the dimensions of the decoder to the vocabulary size, such that the softmax can work properly. That is the main idea why you actually have a linear layer. Now, why am I actually having a softmax layer? It is nothing but, softmax does nothing but, it would just mark everything between 0 and 1. So if I'm actually giving a set of values, whatever be the range of the values, according to their importance, it would actually convert into probabilities, to 0 and 1. So in this vocab size, it would actually give me the output probabilities, that output probabilities is nothing but, now I have my vocab size which is more probable to occur the next word than the other. So that is nothing but my output probabilities that has been actually given by the softmax layer. Now, and accordingly you would actually get your output token. So This is again actually the source of J. I have written it somewhere, but yeah, this is nothing but just the entire architecture, as you can see, where you would actually give a set of inputs to the encoder, and the encoder would actually encode it into key and value vector. Now, this key and value vectors has been given to the decoder along with the input vector. So if I'm actually giving I actually predict the next word am. If I'm giving am, I'm predicting the next word a. So the decoder would actually generate the output according, generate the next word based on this, entire architecture. That is all about the entire architecture according to the paper. There are a lot of modifications of this architecture which has been running as of now, but then according to the paper, this is the entire architecture which has been given. Now, again, why do we actually need self-attention in this scenario? They are actually certain points over here, I should say. The computational complexity, how complex is the calculation. Now, each layer, how complex is the calculations. Now, that is actually been one of the aspects. The amount of computation that is needed, how much of amount of computation that can be parallelized in this set of, let's say I have to do some 56 matrix multiplications. In this 56 matrix multiplications, how much can I actually parallelly do? That is the amount of computations that can be parallelized. The path length between the long range dependencies. So how distant can my I can say dependencies can be. That is on also one of the other aspect that is actually being dealt. Based on these three things, they have actually identified that self-attention being a little more better than the recurrent and the convolution neural networks altogether. Because if you just notice that the maximum path length, which has been mentioned, that the long range dependencies is you can actually have O of 1. So the entire data can actually have the dependencies between one to other. That is the assumption here. Now when you that is the conclusion here, with respect to the sequential of the operation, amount of computation that can be parallelized. Now if I'm having 56 matrices, I can actually do 56 matrix manipulations simultaneously, which is O of 1. That is again easy to actually do. And on top of it, the computational complexity is nothing but how many matrix multiplication should has to be done within a particular layer is the computational complexity. Now in self-attention, it is mostly in and around the number of words present. And in the recurrent and the convolutional neural networks, this is more in and around the dimensions. So that is the reason, when recurrent and convolutional neural networks, it is d squared. The dimensions have been more given, the matrix multiplications are more based on the dimensions, but in the self-attentions, they are more based on the, I should say, the number of words that are present. Now, coming back to training, the data sets that they have actually used, they have used an English to German data set with 4.5 billion sentence parameters. And and data set too, they have actually used English and French and English and German being the data sets that have been used in the attention paper, and they have batched it with 25,000 source tokens and the target tokens. Hardware, they have used certain hardware with 8 NVIDIA P100s at that point of time. And then it took around 4.4 seconds, trained for 12 hours and all. The big model that they've actually mentioned is trained for 3.5 days. The optimizer that they've actually used was an Adam optimizer with the parameters, and the learning rate that they've actually used. Okay, the small modification in the learning rate is that the learning rate initially would linearly increase till a particular step, which is called as warm-up step. And post that warm-up step, it would proportionally decrease. That was the architecture that I've actually designed. Now, the reason why it has actually been done is obviously in the initial stages, you can take a little higher learning rates to get into that gradient descent. And then post after certain periods, you have to little slow down on your learning rates such that you would actually get that global optimum. That is the reason why the learning rates have been actually, the learning rates are actually being chosen in this way. Regularization, residual dropout. So the regularization, they have actually used two kinds of regularization, residual dropout and the label smoothing. Dropouts, they have added between sublayer output and the sublayer input layers, and also between the position sums of positional and the input embeddings. Label smoothing, which is nothing but you would actually pick up some probability from the highest and then give it to the others, such that it would actually make the model to be a little more unsure, but then still the accuracies have actually improved because of the label smoothing architecture. The results, as you can see, the transformer big model was actually performing very good than any of its contemporary models with a very less training cost. Even the transformer base model was actually performing better, but then the transformer big model was actually performing even better. Model variations, what it has actually happened is that they have actually tried upon by changing the number of heads, the number of dimensions, increasing the dimensions, and so on and so forth. So what they have actually noticed is if they have reduced the heads to 1, then the accuracies have decreased, but then increasing heads to a very large extent is also decreasing the accuracies. That is their conclusion. And then obviously, if the dimensions are actually less, then the accuracies are falling down. If the dimensions are high, then the accuracies are actually increasing. Dimensions again is nothing but the learning, the embedding learnings that they want to get into. And the dropouts, if you have dropouts, then the model is actually performing better. And obviously the big model was actually performing better than any of its smaller versions. Generalization, this being one of the important aspects, again, is that they have noticed that once they have trained these transformers, English to French and English to German, transformer, they have noticed that it is performing well in the transformer, in the parsing English parsing task as well. So if I actually give you to parse a sentence within English, then also the transformer could able to do well, though it has not been trained for that particular reason. With a very small data set, with a very small data set, it could able to actually do better it could generalize well for an related task as well. That is one of the important what I should say important feedback they got from this entire thing. And yeah, as conclusion, back then when they've released this particular model, what they've actually felt is this was, obviously this was first model which has completely removed the any concepts of recurrent neural networks or anything of that sort, and then everything has been replaced with the attention models. That being one. The second being, this has been significantly faster than any of the RNNs and CNN architecture because there is no need of you processing it entirely sequentially. So that is being another important conclusion that they actually got, and also outperforms the the previous networks, and also generalizes well, frankly, though they have not mentioned in the conclusion, it was also relatively generalizing better compared to any of its previous specific trained architectures. Then future works at that point of time, again, they have mentioned that transformers can be used to other tasks other than the machine translation, and also to include other modalities like images, videos, and so on and so forth with respect to this the entire can be actually included within the architecture. Was there future work at that particular point of time? Now, if we get into a code a little bit. So, if I actually get into a little nuances of the code, This is firstly the transformer function altogether. This is where they are initializing every weight, where they're using that initialization every now and then. As we have actually seen, this is a feed-forward neural network where we have seen in the architecture, there are two linear transformations and one ReLU activation. So over here, as you can see, they are, it has been initialized with two linear transformations and ReLU activation, and also obviously the dropout layers. So it actually does the similar way, one linear transformation, ReLU activation, dropout, and the second linear transformation. That is what actually happens in the feed-forward neural network. We'll come into multi-head attention. Okay, yeah, anyways. So in the multi-head attention, what we are actually doing is we are taking the input and then projecting it into three linear transformations. So the three linear transformations would actually give me the query, key, and value vectors. And then post that, we are actually taking a linear transformation on the output vector as well. As you've seen, we are actually concatenating all of them and then multiplying with the weight vector. So that linear transformation we are doing in the output vector as well. So, so this is initializing everything, like initializing the weights and all. So in this scenario, this is the scale product attention that we are actually doing, that we are actually multiplying the query and the key value, and then doing a scaling down softmax and all, and then doing a dropout, then multiplying the scaled down version with the value vector, then doing little what I should say, matrix manipulations for it to for the embeddings to be actually being properly projected to the next layer. Then the output layer, again, as we have seen, we are doing a linear transformation on the set of output layers as well. Now, when it comes to an encoder layer, one particular encoder layer, what we have actually seen is the same thing, that we are having a multi-head attention. After a multi-head attention, we had a residual addition and the layer normalization layer. Post that, we are actually having a feed-forward neural network and then a layer normalization again. So that is the same thing that we are actually doing here, that the we would actually take up the self-attention and doing a normalization. So over here it is showing first it is actually doing a normalization of the previous layer and then taking up the attention. So either way, you are actually doing a normalization before you giving it to the next sublayer. So you would actually take up the attention, then drop out the feed forward network. Then again, you're doing a feed forward network normalization and also feed forward network, then again the dropout. So this is what, and also the residual connections, as we have seen, we are actually making sure that the output is again given to the input. Similar to what the decoder layer is, again, we'd actually do this similar steps even in the decoder layer. Now, as I just mentioned, the encoder is nothing but, now what we have seen is an encoder layer. Each layer, what it does, the encoder is nothing but a stacked upon 6 layers. If I'm actually having a number of layers, it would actually stack upon that set of 6 layers, and then would actually do the for each layer, it would actually do the encoding layer. Decoder is something different. It is stacked upon 6 layers on the decoder, and for each it will actually perform the generation, the encoder generation. So this is the entire transformer architecture, wherein you would initially first get the embedding layer for for your target and the input embeddings set. So for the target embeddings, you would actually have the embeddings. Now, if you are actually having the inputs as well, if it has inputs is true, then the input, you would actually set the input, the input embeddings as well would actually be set. And post that, you're setting the, input embeddings and the output embeddings, you would actually do something masking and all for, creating the pads and all for the dimensions and all. Post that, you would actually do encode and decode. Now, what does encode do? is that you would actually take up the positional embeddings, take up the input embeddings, take up the positional embeddings, and then add and then give it to the encoder. Now, encoder would actually take this input embeddings, do all the 6 layers for each encoder layer, and then give the output back again. Similar to what the decoder layer does is it would actually take up the vocab embeddings, the input embeddings, and then it would actually do the one second before this decoder. Yeah, it would actually send it to the decoder, and then post that, as we have actually seen, this is a linear layer which would do the conversion of decoder output to the vocab size. This would actually do that linear layer would actually do the conversion of decoder dimension to the input embeddings. That is what it actually does. And then this is the nothing but you would actually use the sine and cosine function, concatenate them for your, what I should say, positional embeddings. So given a formula, so the formula is all elaborated, and then you would actually get the sine and cosine values to the given for each and every dimension. That is what it actually does, the positional encoding. So yeah, this is all about I should say the the entire workflow of I should say the attention is all you need paper along with the intuition and the code. Hope I'm actually clear. And then yeah, please so Simrat, can we actually take up some of the questions?
Yeah, sure, Marty. Yeah. So I think we covered the positional embedding stuff. Yeah. There was a question on YouTube around softmax, and the user asked something like softmax seems to be important here. Can you please touch a little bit more on that?
Okay. So
So we did cover. Maybe you can just give like a one-liner repeat of why we are doing softmax to map to the vocabulary.
Yes. So softmax, the major reason is nothing but now when I am actually having, so even in this scenario, I should say, I can more represent over here. So even in this scenario, if you see the main functionality of the softmax is nothing but it will convert the values, whatever the values been given to it, in from 0 to 1 based on its importance. So it would just actually give that, the probability, which is nothing but the probability, obviously. So if I'm saying 14, then saying this is more probable. When I'm saying 12, this is saying like this is less probable. So it is just converting the values into probabilities. So I said it is 0 to 1, I can actually compare them easily. The similar is actually what it does, even in the, what I should say, this particular, this particular scenario also, it is a similar that it actually does. I have a linear transformation of the values, the projections to the vocab size. I have some values. Now I have to place them between 0 and 1. That is the main objective of what softmax will actually do.
Right. And there were some questions for comparison with RNN. You've covered that as well. So I think we're good there.
Okay.
And yeah, there was also a question which I think came up through different people. They wanted to understand, like, where does the positional embedding reside? Like, how does it coexist with the word embedding?
What coexists with the word embedding?
So yeah, so the fact that the positional embeddings is actually combined with the word embeddings and created this new unified embedding, right? I think people had that question, although we answered for some of them on the Zoom chat, but also for the YouTube users.
Okay.
I think if you can just cover that bit, like how do these embeddings basically exist? Are they independent? How do they work? Do they, yeah.
Okay. So initially over in the architecture, I should say. So so if you can actually see over here, they are two different embeddings. So input embeddings are different from the positional embeddings. Input embeddings, what I mean is, in the scenario that we have seen, it thinking missions and all, so they would actually have one embedding. Let that be, we'll initialize with Vertex, which usually not it is a general embedding layer, which is usually taken. Let us have a one particular embedding of the inputs. Now the positional embeddings is nothing but which would actually give the positional information about that particular word. So what is positional information again? As I said, if that particular position is in the first place, or if that particular position is in the second place, or if that particular position is in the third place, that is the positional information, which is different from my input embeddings. That is the first thing. Now, second thing is they are being, when given to the network, they are being added and given as one input to the network. So what it intuitively does is, if you see this small graph, so I am actually having an input embeddings present in some place in my entire vector space. Now I am actually shifting my input embeddings to a certain position, shifting to a certain other position based on this positional embeddings. So though my input embeddings is present at a particular place, they're being shifted based on my position, the existence of a position. So what I meant over here is my how, let's say, in this scenario, my how, if this is in the first place. So let that be it is having a certain position embeddings. So now my input embeddings for how can place here. If my same how is present for the fifth or a sixth, fifth or a sixth position, then the position of the how will be somewhere over here. So such that I am actually here giving an intuition to the model that, see the the position of this particular embedding and that particular embedding are different. So you have to learn, though it is a word how, you have to learn them differently. So which means that I am, because transformers doesn't actually process sequentially, that information has to be given to the transformer in some or the other form. That is where, this is where I'm actually, making a little slight differences for my how position. And I'm actually saying that, this position in the first, this word in the first position is different from the same word in the fifth position. I hope I'm clear.
Yeah, and we are over time, but I think we can cover one more question which came from YouTube. We've answered that on Zoom chat, but again, it'll be helpful for the users who are following us on YouTube, which is why 6 layers of encoders and decoders are important and why not 5 or 7? So if you could just touch upon the trade-off between like how did they get to like a specific number of layers, and just a little bit around the trade-off. I think that will also be helpful for the folks.
Okay, so very frankly, I feel intuitively it is just based on the experimentation, because this 6 layers is also for this particular use case, as I just mentioned, right? In this particular actually use case, they are actually taking 6 layers. If you actually get out of this, just the attention is all you need, and then take a general, the set of other, what I should say, other architectures. There are actually 72 encoder layers also stacked upon one on top of the other. So it is I believe it is just based out of experimentation. They are actually coming up with the set of layers.
Yeah, and I just wanted to add to that. Basically, there'll be a very interesting analogy that we can give here, which is like different kernels in CNN. So you're trying to learn something different. Every layer is going to learn something different. Now it's all about the complexity of the problem that you're trying to solve to estimate how many layers you need. Too many layers also mean too much. Like the training gets more expensive and all of that stuff. So it's like a trade-off between how complex of a problem you're solving and how much how expensive do you want your training to get. Do you want it to keep it really simple and under limit?
Yeah. So this part of getting different intuitions is also at the head level as well. Head level also, it can actually learn different aspects, like, the one that you have mentioned, parts of speech dependencies, as well at the layer level. So that is true that, the different intuitions would actually be part of each layer. So it
Yeah,
is just
different
by yeah.
Yeah, makes sense. I think this was a really engaging and interesting discussion that we had on this paper. We are over time and I don't see any other questions. So, Bharat, if you give thumbs up, I think we'll be good to wrap up. All good on YouTube, right? Okay, I think we're good. Thanks, Mati. Thanks everyone for joining us. We had like a really wonderful discussion. Hope to see you guys again on another paper discussion.
Thank you. Thank you
Thank
very
you.
much. Thank you.